Hello everyone. Today is Tuesday, July 28, 2026. I'm your host named Noel. And today, I'm introducing a trending article from the archives. The title is Cross-Tokenizer on Policy Distillation via Byte Prefix Marginalization. The plural is Swiagorojivo sets a 7.22,334. It is long. Why did the tokenizer cross the road? Oh wait. Didn't. Just marginalize. It's byte prefix until the chicken looked like a dog. Moving on. Let us talk about what this paper is actually trying to solve, because it's quite fascinating. In the world of artificial intelligence, we have these massive open weight language models, like Qwen or Qwen. They are super smart, but they are also huge and expensive to run. So researchers want to take the knowledge from these giant teacher models and cram it into the smaller and more efficient student model. This process is called knowledge distillation. Specifically, they use something called on-policy distillation, where the student generates text, and the teacher corrects it along the way. But here is the catch. This usually requires the teacher and the student to speak the exact same language. In AI terms, they need to use the same tokenizer. The tokenizer is just a dictionary that chops up words into smaller pieces called tokens. If the teacher and student use different tokenizers, they chop up the words differently. The standard distillation process breaks down. The student might not understand what the teacher is trying to say, because the token boundaries do not match. Existing technologies, like Logo, try to fix this by matching probabilities, or finding overlapping words, that they often throw away important information, or match things that do not actually mean the same thing. It is like trying to translate French to English by just looking at the length of the words, which obviously does not work perfectly. When the tokenizers are different, the distributions occupy different probabilities, and equal position indices may refer to entirely different text prefixes. This creates a massive headache for engineers trying to train these models. They are forced to only use teachers that share the same tokenizer as the student, which means they might miss out on using the absolute best teacher available for a specific task. Enter Byte Prefix Marginalization, or BPM for short. This paper proposes a brilliant solution. Even if the tokenizers are different, the underlying data is still just a bunch of bytes. Maps the teacher probability mass to the student tokens by looking at the shared byte space. It finds the longest student token that matches the byte prefix of the teacher token. If it cannot find a perfect match, it puts the leftover probability into a special residual category, so no information is ever lost. This means the cavity is vocabulary complete, byte aligned, and mass preserving. It perfectly translates the teacher knowledge into a format the student can actually use. The researchers prove that this turret exactly recovers the teacher-induced byte prefix marginal on more than 99% of the training positions. For the rare cases where a student token spans multiple teacher tokens, they use a clever chain file as lower bound to keep the math sound. Let's compare this to other technologies in a bit more detail. Prior methods either threw away mismatched tokens or aligned them based on rank. For example, a method called SimCleaves unmatched teacher mass completely untransferred, which violates the rule of vocabulary completeness. Another method called fold sorts each distribution by probability and matches it rank by rank. That this means it might assign teacher master student token to a completely unrelated byte content, violating byte level alignment. On the other hand, looks at the raw bytes, ensuring that the meaning is preserved exactly. In the total probability mass, always sums to 1. The researchers tested this by distilling knowledge from 3 different giant models, including the three marks, into a smaller WIN student model. And the results were incredible, then consistently outperformed all the other cross-tokenizer methods, improving performance on math and programming benchmarks by up to 6 points over the strongest baselines. Interestingly, researchers also found a word failure mode during their experiments when training on code generation data at positions where the turret consists purely of white space This byte exact alignment can actually transfer tokenizer-specific segmentation noise instead of the teacher predictive behavior. This basically caused the student model to forget how to indent code properly, dropping its code pass rate from 49% to just 9%. To fix this, they introduced a prep compy mask that simply ignores these all white space turbo positions during training, which completely prevented the collapse. It is those little practical details that make a huge difference in AI research. You might be, how does this apply to everyday life? Well, let me give you 3 specific application examples. Imagine having a super smart AI assistant directly on your smartphone. Right now, the really capable models are too big to fit on a phone, so they have to run in the cloud. This means you need an internet connection. There's always a slight delay when you ask a question, but then, companies can take the immense knowledge from multiple massive cloud models and distill it down into a tiny and highly efficient model that runs completely on your device. You would get lightning fast and incredibly smart responses without needing the internet at all, and it would save a ton of battery life. This could revolutionize how we interact with mobile devices daily. Second, think about coding assistants like GitHub Copilot. These tools are fantastic for developers, but they can be slow and incredibly expensive for companies to host on massive server farms. By using BUM, a company could train a much smaller coding model that still retains the complex reasoning capabilities of a giant teacher model. This smaller model could be integrated directly into your local code editor, providing instant suggestions and debugging help, even on older or less powerful laptops. It makes high-level programming assistance accessible to everyone, not just those with access to massive cloud servers, which could drastically speed up software development worldwide. Let us talk about smart home devices. Your smart speaker or smart thermostat currently relies on very basic AI, or has to send your voice data to a server to be processed. With this Cross-Tokenizer distillation, manufacturers could embed highly capable reasoning models into cheap and low-power smart home chips, where smart home would be able to understand complex and multi-step commands, like asking it to dim the lights when a movie starts, but only if it is past 8 at night. And it would do all of this locally, keeping your personal voice data private and secure within your own home. So, this paper is not just some abstract medical theory. It is a very practical stepping stone to making powerful AI smaller, faster, and much more accessible for all of us. It is really cool stuff. Thank you for listening, and I will see you next time.